measured quantities are almost never exact. In the sciences, it's understood that a quantity like 1.23 meters actually has a little bit of uncertainty in it. And the standard practice is that in a quantity like this, all of the digits are certain except for the last one. The last digit is uncertain. In this case, our best guess is that the last digit is 3, but the measurement might actually be 1.22 meters, 1.24 meters, possibly even 1.21, 1.27. But our best guess is that it's 1.23, but we're not quite sure about the 3. The 3 is uncertain. And if we want to do math with uncertain quantities like this, we need to take that uncertainty into account. So let's look at what would happen if we were to add 1.23 meters plus 0.045 meters. So maybe we had a garden gnome that was 1.23 meters tall, and we put a hat on his head that was 4.5 centimeters tall, and we wanted to know the total height. That would be 1.23 meters plus 0.045 meters. Now, if we just take those quantities, just take those numbers and type them into our calculator, we get a total height of 1.275 meters. And then we can ask ourselves, which of those digits are we certain about? Which are we uncertain about? There's a couple ways that we could think about this to help us answer that question. One way that we could think about it is if we were to write the sum in this way, 1.23 plus 0.045. If we think about the uncertain digits, this 3 is uncertain, this 5 is uncertain. And I think you can see that when we add these numbers together, that both the 7 and the 5 are uncertain. If the 3 were to change, or the 5 were to change, both the 7 and the 5 could be different numbers. But we're certain about the 1 and the 2. So in our answer, the 7 and the 5 are uncertain values, the 1 and the 2 are certain. Another way that we could think about this is 1.23 meters actually represents a range of values. We're not sure how big that range is, but if we want to look at the effect of uncertainty in the 3, we might try raising and lowering that last digit by 1. And so we might say that 1.23 could easily be any number in the range of 1.22 to 1.24. It could probably be higher or lower than that, but this will give us a way to see how the uncertainty affects the numerical answer here. Likewise, the 0.045 could easily be in the range of 0.044 to 0.046. And if we look at the range of possible sums of these numbers, the highest that the sum could be is 1.286. The lowest that it could be is 1.264. And so looking at this range, we can see, again, the 1 and the 2 are exact. We know those numbers, but the last 2 digits are flexible. We don't know exactly what those digits are going to be. So again, in our answer, we're certain about the 1 and the 2. We're not certain about the 7, 5. And so when we round this off to give our final answer, we'd want to round it off so that we only have one uncertain digit. So we'd round it off to 1.28 meters. And so the rule that we're using here, the rule when you're adding and subtracting numbers that have where the last digit is uncertain, is you look at the decimal place, the uncertain decimal place of the numbers. So in our first number, the second decimal place is uncertain. In the second number, the third decimal place is uncertain. And since uncertainty in the second place will have more of an effect than uncertainty in the third decimal place, our answer is going to be uncertain in the second decimal place. And so the rule is that when you're adding or when you're subtracting numbers, you look at the precision, you look at the number that has less precision in the decimal places, and that determines the precision of your answer. Now, what about multiplication and division? Well, let's say that we had a sample of, say, argon. Maybe we had 0.19 moles of it, and we want to know how many grams that corresponds to. Well, just multiplying out 0.19 times 39.95 gives us 7.5905 grams. And we should ask ourselves which of those digits are certain and which of them are uncertain, so that we can round off this value to an appropriate precision. And so, again, one way that we can think about this is if we think of a range of values for the two numbers that we're multiplying. 0.19, if that 9 is uncertain, that could easily be in the range of between 0.18 and 0.20. Likewise, the 39.95 could easily be in the range of 39.94 to 39.96. Again, it could be outside that range, but we're interested in seeing how that uncertain digit affects our answer, and so just tweaking that digit a little bit will give us a way to check that. And if we look at this multiplication now, the highest value that we could get when we multiply numbers in these ranges is 7.9920. The lowest value that we could get is 7.1892. And looking at this range of possible answers, we can see that the 7, we're certain about that. We know the number starts with 7, but all of these decimal places we're not sure about. So in the answer to our original multiplication, the 5905, all those digits are uncertain, and so when we round this off, we want to round it off so that we only have one uncertain digit, and so we would round this off to 7.6 grams, and that would be our final answer. So the rule that applies in calculations like this, when you're multiplying or dividing numbers, is you look at the number of significant figures in the numbers being multiplied or divided. So here we've got 2 significant figures in the 0.19 moles. We've got 4 significant figures in the 39.95 grams per mole. And the number with less precision is the first number of the 2 significant figures. That's going to determine the precision of our answer. Our answer will have 2 significant figures. Okay, I want to look at an example from real life. So back when I was teaching undergraduate chemistry, one of the experiments that we would do in the laboratory would involve a glass bulb that had a little valve on it, and we would precisely weigh the bulb, figure out its mass, and then we would fill the bulb with a sample of gases and use it to do a bunch of experiments. So we'd make a bunch of measurements of the bulb, and then at the end of the experiment, we wanted to figure out what the volume of gas in the bulb was. And the way that we would do this is we would take the bulb, we'd fill it up with water and weigh it, and then by subtracting the weight of the bulb with water minus the empty bulb, that gives us the weight of the water inside the bulb. And then since we can look up the density of water, we can figure out the volume that the water took up inside the bulb, and that's going to match the volume of the gas inside the bulb. And that was what we were looking for. So let's look at how calculations would work in this experiment. So when we weighed the empty bulb, the bulb was light enough that we were able to use a fancy electronic balance that gave us 4 decimal places of precision. And so one of the times that we did this measurement, the empty bulb had a mass of 90.2403 grams. Now, when the bulb was filled with water, unfortunately, it became too heavy to use on the really precise electronic balance. It would overload it. And so the filled bulb, we had to weigh on a cheaper balance that didn't have quite as many decimal places. And in one of the measurements, the mass came out to be 286.81 grams. And so when we set about subtracting these to find the mass of the water, we would have the mass of the bulb with water, 286.81 grams, minus the mass of the empty bulb, 90.2403. And just typing those numbers into a calculator gives a difference of 196.5697 grams. And then we would need to round this off. And we've talked about how we round this off dealing with the subtraction, but let's look at this in terms of the uncertainties and the ranges of values. So our first number, the 286.81, the 1 is uncertain, and so that number could reasonably be anywhere from 286.80 to 286.82. And then we're subtracting this number where the 3 is uncertain, so that could reasonably be between 90.2402 and 90.2404. And subtracting those, the largest that the difference could be using those numbers is 196.5798, and the smallest that it could be using those ranges is 196.5596. So looking at these the ranges in the possible answers here, the 196.5, those digits are certain. We're sure that that those are the first 4 digits of our answer, but the rest of the digits we're not sure about. There's some variability in those digits. And so the answer that we got on our calculator, the 196.5697, those final digits, the 697, are all uncertain. We would want to round this off so that there's only one uncertain digit. And so in this case, we would round it off to 196.57 grams, and that would be our answer. And so again, here we've got a subtraction, and the rule for adding and subtracting quantities is that you look at the number of decimal places of precision in the numbers. So in our first number, the second decimal place is uncertain. In the number we're subtracting, the fourth decimal place is uncertain. So the first number has less precision in its decimal places, and so that's going to determine that our answer will have 2 decimal places of precision. The second decimal place is uncertain. So that's how we would work out the subtraction part of this calculation. And then on the second part, going from figuring out the volume of the water, which is the same as the volume of the interior volume of that glass bulb, the way that we did that is volume is equal to the mass of the water divided by the density of water. And we just found that the mass of the water was 196.57 grams. The density of water at the room temperature when we did the experiment is 0.9982 grams per milliliter. Typing these numbers into our calculator gives a volume of 196.924 milliliters. And again, not all of those digits are going to be certain, and we can see that if we look at ranges that these numbers could have. The 196.57, that uncertain 7 means that that value could easily be in the range of 196.56 up to 196.58. And then we're dividing by this number where the uncertainty in 2 means that it could easily have be anywhere in the range of 0.9981 up to 0.9983. And if we divide numbers in those ranges, the highest that the quotient could be is 196.954. The lowest is 196.895. And so we can see, looking at this range of quotients here, the 196, those digits we're sure about, but everything after that is not so sure. And so in our calculated answer, the 0.924, all of those digits are uncertain, and we would want to round this off so that we only have one uncertain digit. And so in this case, that would round to 196.9 milliliters. And so again, the rule when you are multiplying and dividing numbers is that you look at the number of significant figures in the numbers being multiplied and divided. So in this case, we're dividing a number that has 5 significant figures by a number that has 4 significant figures. 4 significant figures is less precision than 5, and so it will determine the precision of our answer. Our answer will have 4 significant figures. So to summarize these kinds of calculations, first of all, using significant figures gives us a way to indicate numerical precision. So it gives us a way to express the idea that measured numbers are not exact. There's always a little bit of uncertainty in those values. Significant figures include all certain digits of a number and then one uncertain digit. So the last significant figure is always an uncertain digit. All the other digits are certain. And when you're doing a calculation, the precision of a calculated value always matches the least precise input number. And so in the case of addition and subtraction, the precision that we care about is the number of decimal places in the numbers that we're adding or subtracting. And when we're multiplying and dividing, the precision that we care about is the number of significant figures in the numbers that are being multiplied and divided. And that's it for today.